The next two videos are on so-called improper integrals. These can be found in section 6.5 of the book. Now, what is this about? Well, what we have considered so far are indefinite integrals, which are primitives, and definite integrals. Now, what was a definite integral? It's the integral of a continuous function f over a finite interval from a to b. And in this case, this definite integral exists. And we compute it by computing the primitive, evaluating the value of the primitive at the points a and b, and subtracting the value at b minus the value at a. Now, of course, we can have a number of variants, namely which occur in the case of probabilistic examples. So, first variant is when one of the boundaries of the interval is infinitely large. That means that the left boundary a is equal to minus infinity, and or the right boundary b is equal to plus infinity. Another variant may happen when f of x itself is not defined at one of the endpoints. So, for instance, f of x converges to plus or minus infinity as x approaches either the left point of the interval from the right, clearly, because we are only looking at the interval ab, or to b from the left. Now, in this case, if this happens, we call the corresponding integrals improper integrals. Now, let's look at type 1. And we have a theorem there in the section 6.5. And suppose that f is continuous on the interval from a to infinity. Now, what we do is define the integral from a to infinity of this function f as the limit for r to infinity of the definite integral over the interval a to r of f. Call this I. Now, so of course, two things can happen. This limit I exists and is finite. Then we say that the improper integral from a to infinity of the function f is convergent, and the value is equal to I, or this limit does not exist, or maybe infinitely large, because then we also say that it doesn't exist, and we call this improper integral divergent. And we have no answer in this case. Now, clearly, we only discuss the case where the right endpoint is infinitely large, but we can do a similar definition. We can give a similar definition in case the left point is infinitely large, or if both endpoints are infinitely large, and we have the integral from minus infinity to plus infinity of the function little f. What you have to do in this case is just split the integral into two parts, from, say, minus infinity to 0, that is arbitrary, and a part from 0 to infinity, and consider both of these terms separately. Let me give an example. So suppose we wish to calculate the integral from 1 to infinity of the function 1 over x squared. Now, formally speaking, this is equal to the limit for r to infinity of the integral over the interval 1 to r of the same function. And if we calculate that definite integral, we get that the primitive of 1 over x squared is minus 1 over x. You know this already. We should evaluate it at the points r and 1 and subtract these. And we get minus 1 over r minus 1. Now clearly we have to take limits. And so the limit for r to infinity of minus 1 over r is equal to 0. And so we are left with the contribution of minus 1 equals 1. So we have a finite outcome. That means that the improper integral is convergent with limit 1. Now in general we do this a little quicker. So what do we do in general? We suppose that capital F is the primitive of little f, so capital F prime is equal to small f, and we just check that the limit for r to infinity of the function capital F evaluated at r is finite, and what we do is write we write directly that this improper integral is equal to the value of capital F at the points a and infinity, where we in fact interpret that the value at infinity is simply the limit for r to infinity of f of r minus the value at a, and this is how you would generally write it.